Welcome to this lesson on acids and bases for IB Chemistry Higher Level. In this lesson, we will cover the Arrhenius, Bronsted-Lowry, and Lewis theories of acids and bases, strong and weak acids, pH and pOH calculations, buffers, titration curves, and the equilibrium aspects of acids and bases. Let's begin with the three main theories of acids and bases. The Arrhenius theory defines acids as proton donors producing H+ ions in water, and bases as hydroxide donors producing OH ions in water. This is limited to aqueous solutions. The Bronsted-Lowry theory is more general. An acid is a proton donor, and a base is a proton acceptor. This introduces conjugate acid-base pairs. The Lewis theory is the most general. A Lewis acid accepts an electron pair, and a Lewis base donates an electron pair. This includes species like boron trifluoride that don't have protons. Understanding these theories helps you identify acids and bases in different contexts. Acids are classified as strong or weak based on their degree of ionization. Strong acids completely dissociate in water. The 6 strong acids are hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, and perchloric acid. Weak acids only partially dissociate, establishing an equilibrium. Examples include acetic acid, carbonic acid, and citric acid. The strength of a weak acid is measured by its Ka value, the acid dissociation constant. A larger Ka means a stronger acid. For very weak acids, we use pKa, where lower pKa indicates stronger acid. The same concept applies to bases, with strong bases being hydroxides of group 1 and 2 metals. pH is a measure of hydrogen ion concentration, defined as the negative logarithm of H+ concentration. pH equals negative log of H+ concentration. For strong acids, pH equals negative log of acid concentration. pOH measures hydroxide ion concentration. The relationship is pH plus pOH equals 14 at 25 degrees Celsius. For very dilute solutions, we must consider the autoionization of water, which contributes 10 to the -7 moles per liter of H+ and OH. pH can be calculated for strong acids and bases, but for weak acids, we need to use Ka and the quadratic formula or approximation method. Remember to check if your approximation is valid by comparing calculated H+ to initial acid concentration. Salts are ionic compounds that can produce acidic, basic, or neutral solutions depending on their constituent ions. Cations from strong bases, like sodium and potassium, do not hydrolyze and have no effect on pH. Cations from weak bases, like ammonium, hydrolyze to produce H+ ions and make solutions acidic. Anions from strong acids, like chloride, do not hydrolyze. Anions from weak acids, like acetate, hydrolyze to produce OH ions and make solutions basic. Salts of weak acids and strong bases are basic, salts of strong acids and weak bases are acidic, and salts of strong acids and strong bases are neutral. This is essential for predicting the pH of salt solutions. A buffer solution resists changes in pH when small amounts of acid or base are added. It consists of a weak acid and its conjugate base, or a weak base and its conjugate acid. The Henderson-Hasselbalch equation allows us to calculate the pH of a buffer. pH equals pKa plus log of conjugate base concentration over acid concentration. Buffer capacity depends on the concentration of the acid-base pair. The more concentrated the buffer, the greater its capacity to resist pH changes. Common buffer examples include acetic acid with sodium acetate and ammonia with ammonium chloride. Buffers are crucial in biological systems, industrial processes, and analytical chemistry. A titration curve plots pH against volume of titrant added. The equivalence point is where moles of acid equal moles of base. For strong acid, strong base titrations, the equivalence point is at pH 7. For weak acid, strong base, it's above 7. For strong acid, weak base, it's below 7. The half equivalence point is particularly important for weak acids. At this point, pH equals pKa. This allows us to determine Ka experimentally. Indicators are chosen based on the pH range of the equivalence point. Phenolphthalein is suitable for strong base titrations, while methyl orange works for acid titrations. Acid-base equilibria are described by several important constants. Ka is the acid dissociation constant. Kb is the base dissociation constant. Coa is the ionic product of water, which equals H plus times OH and equals 10 to the minus 14 at 25 degrees Celsius. These constants are related. Ka times Kb equals Kw. This means if you know Ka, you can calculate Kb, and vice versa. The relationship pKa plus pKb equals 14 also holds. For polyprotic acids, each proton has its own Ka value, with Ka1 being much larger than Ka2. Understanding these constants helps predict the strength of acids and bases and their position in equilibrium. The Lewis theory extends acid-base chemistry beyond proton transfer. A Lewis acid is an electron pair acceptor, while a Lewis base is an electron pair donor. Metal ions are classic Lewis acids, forming coordinate bonds with water molecules to create hydrated metal ions. Aluminum chloride is a Lewis acid, accepting electron pairs from chloride ions. Boron trifluoride reacts with ammonia because boron trifluoride is a Lewis acid and ammonia is a Lewis base. This theory is particularly useful in explaining the behavior of complex ions and the catalytic activity of certain compounds in organic reactions. Let's review with some practice questions. Question 1. Calculate the pH of 0.1 molar hydrochloric acid. Question 2. Explain why ammonium chloride produces an acidic solution when dissolved in water. Question 3. A weak acid has Ka equals 1.8 times 10 to the minus 5. Calculate its pKa. Question 4. Describe how a buffer maintains pH when small amounts of acid are added. These questions test the key concepts covered in this lesson. To summarize the key points. First, Bronsted-Lowry theory defines acids as proton donors and bases as proton acceptors. Second, strong acids completely dissociate, while weak acids partially dissociate. Third, pH equals negative log of H plus concentration. Fourth, buffers resist pH changes and can be calculated using the Henderson-Hasselbalch equation. Fifth, titration curves show the relationship between pH and volume added, with the half equivalence point giving pKa. Sixth, K, Kb, and Kw are related constants that describe acid-base equilibria. Practice these concepts with past paper questions to ensure exam success. Thank you for watching this lesson on acids and bases.